Hi, my name is Fabio Maschi and I'm a PhD student at ETH Zurich. It's a pleasure to present the work we have carried out in collaboration with Amadeus. This talk is about how to use hardware accelerator in a meaningful way in the context of search engines. This is the Amadeus Flight search engine. It's a very complex, distributed system. Each component is highly specialized, tuned to meet high performance requirements. Scalability today is solved by using several hundred of computing nodes, a costly deployment operation which could be more efficient and effective. So, when you for a flight, let's say from Zurich to Boston, the search engine must explore not only direct flights, but also all the possible combinations of connecting flights. For each pair of these flights, we must filter impossible connections. By impossible connections, we mean that there is a minimal connection time between the arrival of a plane and the departure of the connecting flight. This time must be respected and comes from logistic issues such as whether there's a passport control, which terminals you're navigating through, or the aircraft size, for example. A total of 22 criteria influence this decision in the real scenario, and airlines update them on a daily basis. We will focus on retrieving the minimal connection time, which is executed within the Domain Explorer. For the sake of illustration, let's suppose the MCT depends only on these four criteria. Therefore, we could have a first rule stating that at Zurich Airport, for an international connection at any terminal and time of the year, the minimal connection time is 90 minutes. Then we could have a second rule stating that at Zurich Airport, if you have a Schengen connection at Terminal 1, then the MCT is only 25 minutes. And so on. Each rule would create a unique combination of values, being more precise or more generic. Here we have the illustration of a classic business rule management system, where queries just state their predicate, and the result is based on the restrictions imposed by the rules. In this case, the minimum time allowed for a flight connection to be feasible. To understand the magnitude of the problem, here are some key figures. There are more than 130,000 rules, and the MCT component consumes about 40% of the CPU time. The current throughput is in the order of a million queries per second. The problem is that it's very expensive to scale in terms of throughput and number of rules. So our goal is to use hardware acceleration to replace the current CPU implementation of the module by a more efficient system in terms of computing resource and performance. An additional motivation is that if we reduce the latency of the system, we can increase the quality of the results. We first focused on the data structure behind the system. How can we efficiently store and navigate through 100,000 rules? The computing cost of inferring the result comes from the actual matching operation between the criteria. So what we want here is to reduce the number of matches and try to filter as early as possible the maximum number of rules that don't apply to our query. For this, we came up with a non-deterministic finite state automata, basically a graph where all the rules share the same origin. Transitions correspond to a matching operation, and the contents are placed as the leaves of the graph, in such a manner that rule 0 would be mapped as this specific path between origin and content. And so would rule 1, rule 2, and so on. Every single rule would be mapped as a specific path between the origin and one leaf, and every level of the graph corresponds to the evaluation of a single criterion. Now, the order in which we evaluate the criteria is not important, since the rules are just a conjunction of operations. However, this order does matter for the shape of the NFA we generate. For example, using exactly the same rule set, the NFA shape can be completely different if we sort the criteria in a different order, possibly requiring more transitions and states. This leads to a different memory requirement and also to a different navigation performance. To perceive the real impact of this, let's have a look at the MCT rules used by Amadeus. The NFA is too big to be plotted here, so let's use this table. The first line corresponds to the origin of the graph. Then, the next ones correspond to a criterion each. So for every line, we have one level of the graph. Finally, the bottom line corresponds to the leaves, so the MCT value pointed by the rule. If we use a random order, such as this one here, the generated NFA would have more than 340,000 transitions, which are the elements we store. In order to reduce it, we have to foster node sharing. So we decided to sort the criteria based on their cardinality. And with the same rule set, we reduced the number of transitions by 27%. But storage is only one static metric. We checked then the worst case to reach a leaf, which models the latency to traverse the graph. Similarly to a database query optimization, we try to filter as early as possible paths that won't lead to an actual match. For this, we place first high selectivity criteria. Also, we place last those that may trigger a higher number of paths. In between, we sort the criteria based on their cardinality again. By doing so, we had a slightly higher memory consumption than the previous ordering, still lower than the random one, but a drastically lower worst case to traverse the graph. And this is the heuristic we decided to use for the experiment. So, with this data structure, how can we explore its parallelism degree to accelerate the evaluation? As we saw, the depth of our graph is fixed by the number of criteria. So, whenever a query arrives, we can allocate the specific criteria to the corresponding level. Then, for each level, we can have an NFA processing element, which will perform the evaluation for that specific criterion. Each processing element is connected to its own memory component, which stores only the transitions for that level. With these settings, each processing element is independent to evaluate a different state of the graph. And you can see what we have here. It's nothing more than a pipeline, where each stage evaluates a different level of the graph, and therefore a different criterion. In between the processing elements, we put some buffers to avoid stalling the pipeline, as they have different progressing speed. On top of that, we have another FIFO to buffer the next queries. And finally, the result aggregator, which is responsible for retrieving the most precise rule that has been matched. Let's see with a simple but practical example how this engine works. Imagine we have this query. As soon as it arrives, the first processing element can start the first level evaluation. As it is a match, it activates the Zurich state. The second processing element can then start processing the second level transitions. And notice that at this point they are both processing different transitions in parallel. The first PE is done, and the second has just activated a new state, allowing the third one to start the evaluation. So again, second and third PEs are working in parallel, as long as there are transitions to be processed. By the time we reach a leaf, the MCT is returned. As soon as the first PE is done with this query, it is free to start evaluating the next one. This is the pipeline nature of our hardware design, taking advantage of the parallel degree of our data structure. To benchmark and evaluate our design, we placed 16 engines on an FPGA board. On premises, this was done using the Xilinx Alveo boards. On the cloud, we used the Amazon F1 instance. Two baselines were used as performance references, a multi-thread CPU implementation of our NFA structure, and Druze, a complete and open-source business rule management system used by Amadeus in other applications. For further experiments, I invite you to check our paper. Here we have the execution time and the throughput for the baselines and the FPGA design as a function of the batch size. A batch being a number of grouped MCT requests. Be aware that some axes are on log scale. We can see that for very small batch size, the FPGA version suffers from the communication overhead imposed by the PCIe bus. For larger batch sizes, however, the FPGA has enough workload to leverage its huge compute capacity and compensates for the PCIe overhead. For a relevant dimension of batch size for the MCT use case, the FPGA design is almost 3 orders of magnitude faster than the fastest baseline, and can deliver 800 times more queries per second than the multi-threaded baseline. Such a performance allows a 2-dimension reorganization of the computing resource in the search engine. One single FPGA would be able to handle the throughput of several CPU nodes. On the other side, for the same workload, The quality of the search could be enhanced by exploring more routes per user request in the same response time. What I would like you to remember from this talk is that search engines with high performance requirements can profit from FPGA acceleration and get significant gains in performance and efficiency. The key to achieve it is a hardware-software co-design. Currently, Amadeus is working on a proof of concept to integrate our design into their system, a required step to be able to deploy it in production. This allows them to experimentally assess the gains versus the cost of porting a completely new system into their legacy architecture and resources. If you'd like to know more, please be in touch with us. You may also find the source code of the engine available on our GitHub repository. Thank you very much for your attention.